Let's do an example using some of this vocabulary that we saw on the previous slide. Growing tomatoes. Does adding fertilizer affect the productivity of tomato plants? How about the amount of water given to the plants? To answer these questions, a gardener plants 24 similar tomato plants in identical pots in his greenhouse. He will add fertilizer to the soil in half of the pots. Also, he will water the plants with half a gallon of water per day, a gallon per day, and 1.5 gallons per day. At the end of 3 months, he will record the total weight of tomatoes produced on each plant. Identify the experimental units, the explanatory variables or factors, the levels of the factors, the response variable, and the treatments. All right, here we go. So first, the experimental units. So these are the things that we randomly assign the treatments to. We had 24 similar plants, and we are going to randomly assign the treatments to each of those plants. I'm assuming that's what we're going to do. 24 plants, so we'll just call them 24 individual tomato plants. How about the explanatory variable? The explanatory variable, or the factors, are the variables that we're modifying, that we're changing to see how it affects something. So we are actually doing amount of fertilizer, and amount of water. You should word these as variables. Don't say fertilizer and water, or 0.5 water, or 1 gallon of water. It's how much fertilizer we're using and how much water we're using. Those are variables. Zero amount of fertilizer, some amount of fertilizer. The levels. So the levels of fertilizer are none or zero, so no fertilizer. And it doesn't really say how much fertilizer we're using. I guess we'll say the recommended amount of fertilizer. You could actually summarize this as yes versus no. Yes fertilizer or no fertilizer. That would be the levels. Or you could talk about the amount. And then H2O, amount of water, we're using 0.5 gallons, 1 gallon, and 1.5 gallons. So we got 3 levels of water. The response variable. Response variable is the outcome we're measuring. This is going to be the total weight, the weight of tomatoes produced by each plant. The last one is the treatments. So again, the treatments are the specific conditions applied to the individual. So the treatments are not fertilizer or no fertilizer. To each plant, you assign a fertilizer level and a water level. So you have to look at every combination of the two. So no fertilizer and 0.5 gallons of water. No fertilizer and 1 gallon of water. No fert and 1.5 gallon. And then our fertilizer treatments. Fertilizer, yes. 0.5 gallon, yes, fert. 1.5, yes, fert. 1.0 gallons. So we actually have 6 different treatments. So if we had 24 plants, we would divide 24 by 4. We're going to randomly assign these treatments to 4 of the plants. That's what we would probably want to do if we were running this experiment, perhaps. And the reason we do this is we can now see not just if the fertilizer is effective or not, But if the fertilizer is effective with certain combinations of water, maybe if you just water the plants enough, they're going to be okay. Or maybe if you use fertilizer, you can see that, well, fertilizer is good, but there's an optimal amount of water that you should do with the fertilizer. Or maybe just more is better. I don't know. But that's what they're trying to figure out, and that's what this experiment will tell them. Experimental design. Suppose we want to design an experiment to see if caffeine affects pulse rate. So if you take caffeine, does it change your pulse rate? Here is an initial plan. We're going to measure initial pulse rate when a student starts class. So at the beginning of class, we're going to measure your pulse rate, every student. We're going to give each student some caffeine. We're going to wait a specified amount of time. We're going to make another final pulse measurement, and then we're going to compare the initial to the final. Okay. Now, in class, we talked pretty extensively about what are the problems with this plan, and what other variables are most likely to be sources of variability in pulse rates. So we had some discussion on this. Obviously, it's hard to have discussion on a video, but I can and maybe you can think of some of these things, but some problems would be, well, you're measuring pulse rate when kids come to class. Maybe they ran up the stairs and had high pulse at the start of class. Then after they rest, even though they took caffeine, their pulse rate might go down. You might say caffeine lowers your pulse rate, but really has nothing to do with the caffeine. It has to do with the fact that you ran the class and then you sat down listening to a boring lecture and your pulse rate dropped to practically nothing, right? Doesn't make sense to give everybody caffeine. If we give all kids caffeine, we really don't have anything to compare. You give everybody caffeine, if they all go up, or how are we going to know if they went up because of the caffeine or if they went up because of something else that happened between the start of class and the later on in class? I mean, who knows what could happen? Maybe there was an announcement. Maybe something exciting happened during the lecture, and that was the cause of it going up. So we don't have multiple treatments that we're comparing to each other. Yeah, there's a lot of different things. What other sources of variability could come into play? Maybe one kid, I don't know if we're giving them a soda, I don't know how we're giving them caffeine, drinks one sip of caffeine soda, and another drinks a 2-liter bottle. So if different kids are doing different things, and we're gonna talk about controlling other variables here down the road, but there's a lot of variability. What if some kids eat breakfast? If they have a big breakfast versus kids that don't eat breakfast. What if half of the kids went to Starbucks in the morning? What if they had caffeine before the experiment, before class? So their pulses might already be high when they come to class because they had some kind of espresso whatever, There's just a ton of variables, a ton of things that can influence your pulse rate. And if we don't run a proper experiment, then we're not going to know. Go back to our previous slide here. 2 slides, I guess. We're not going to know if the caffeine is causing the change in the variable, the change in your heart rate, or if it's these other variables. All of these other variables are being confounded with your caffeine treatment. Okay, so we really can't draw a good conclusion if we do this experimental design. But I think we can come up with a better experimental design to try to get to the heart of our question and see if caffeine really does cause an increase in heart rate. So to address these problems and others, here are the 4 important factors or pillars of good experimental design. If you're going to do an experiment, you have to consider these 4 key ideas. 1, comparison. 2, control. 3, randomization, and 4, replication. So we've already used a couple of these words here, and you probably know what some of them mean. Let's talk about each one individually. Comparison. You must have multiple treatment groups so you can compare the responses under each of those treatments. You could have multiple explanatory variables, factors, multiple levels of one explanatory variable, or one level of one explanatory variable and a control group. So these are kind of like just some different examples. Multiple explanatory variables, that's going to be a really complex experiment. You could have multiple levels from one explanatory variable. So you could just have, I'm going to test caffeine, not caffeine and anything else, but I'm going to test whether you drink a little caffeine, a lot of caffeine, a medium amount of caffeine, or no caffeine. That would be 4 different levels. Or you could just have one level of one explanatory variable and a control group. That's probably what we would have here. We would say caffeine or no caffeine. So this would be the control group. A control group is a group that is used to provide a baseline for comparing the effects of other treatments. Depending on the purpose of the experiment, a control group may be given an inactive treatment, such as a placebo, an active treatment, or no treatment at all. So I think we're going to talk about placebo later, but you guys probably know what a placebo is. But a control group, basically, it's like the status quo. Like we're imposing caffeine on some groups, and we're not going to give any caffeine to the other group. Okay. Note, a control group is a treatment. Let's not forget that. In fact, on the last AP test, there was a question that caught a lot of kids because they said the control group wasn't a treatment. Nope. The control group has nothing to do with the control pillar of a good experimental design. We're going to talk about that control later, but be careful about control being in both of these words. A control group is a comparison group. We conduct an experiment to see if and how studying and eating breakfast causes a change in your grades for an economics test. Identify the different ways we could set up comparison groups or treatments. Okay, so we're conducting an experiment to see how studying and eating breakfast causes. So we got 2 factors. We got study and we have breakfast. I guess we could do different levels. We could say you study or you don't study, or you could say you study 0 hours or 2 hours, or you study 4 hours maybe for this test. And breakfast, you could say no breakfast, so no food. You could say a light breakfast. You'd have to define what light is. Light food or a big meal. So we could set it up like this, in which we have 2 factors and 3 levels for each factor. So the treatments would be 0 hours and no food, 0 hours and light food, 0 hours and big meal, etc., etc. That's one way to do it. And now, do we have a control here? I mean, I don't know if it matters if we talk about a control group here. I guess, is 0 hours the control group? I guess so, maybe. Is no food the control group? Don't worry too much about, well, not to say you should worry about it. You don't always have to have a control group. Like if you're testing different diets, like not in this case, but what type of diet? Like you could have a seafood diet or an Atkins diet or a high carb or a low protein. So the control group would then be no diet. So you're going to test weight loss on all these different diets, and one of the groups you're going to give the control group you're going to give no diet at all. Well, no food. Well, the person would not be able to live without food, But maybe the control group is just keep eating however you've always eaten, So identify the different ways we could set up this comparison group. So, well, this is one way. I'm trying to think of other ways we could do it. Yeah, I don't know. That sounds good to me. I guess maybe I was thinking about like studying. You could study yes, or you could study no, or you could breakfast, you could eat yes, or you could not eat, with the idea that maybe these are the control. So this would be a more simple study, yet less treatments. maybe we could talk about the advantages and disadvantages of these, but I don't really want to do it right here right now. So, okay. All right. Let's go on to control in the next video.